Hi, I'm Mohsen Alizadeh Noghani, and in this video, I will present our IROS and REAL paper, Design and Validation of a Smartphone-Based Haptic Feedback System for Gait Training. In the United States, older adults form about 17% of the population, which is projected to increase to 21% by 2030. Meanwhile, more than a third of the older adults demonstrate gait abnormalities, which if remain untreated will lead to adverse health outcomes such as risk of fall and loss of mobility. Therefore, maintaining an efficient and functional gait is a critical prerequisite for high-quality independent living. Among those gait problems, reduced walking speed is particularly important. Decline in walking speed is linked to a higher risk of mortality. In contrast, increases in walking speed are associated with reduced risk of death, even after accounting for factors such as medical and psychological conditions. Therefore, rehabilitation for increasing walking speed has been recommended for improving the health of older adults. Specifically, results from the literature show that instead of targeting the muscular system, the focus should be on motor learning interventions for training the perceptomotor system. In terms of high-level spatiotemporal parameters, decrease in walking speed can be due to reduced stride length or cadence. But it has been found that the decline in walking speed with age is associated with reduced stride length, not cadence. Therefore, increasing stride lengths can be a viable mechanism for improving walking speed of older adults. However, there is a gap in the literature in that we don't know which lower level parameters should be trained for increasing stride lengths. The next question is, if we are able to identify parameters for training, how can we provide feedback to the user? As a substitute for verbal feedback by an expert, augmented feedback can be utilized. Augmented feedback is divided into three categories of haptic, visual, and auditory, and has shown promise for motor learning tasks. Among those three groups, haptic feedback is particularly useful for training outside of a controlled lab environment, as it does not directly interfere with the situational awareness of the user. Vibrotactile haptic feedback can be achieved by using shaftless eccentric mass motors, which are inexpensive and compact. Further, it has been used in different training systems for modifying a variety of gait parameters. However, there is a lack of a system that can enable regular and independent home-based training. In this paper, we address the two mentioned gaps. Specifically, biomechanical parameters to increase stride lengths were identified. Further, we developed a variable, modular, and wireless haptic feedback system that uses a smartphone as the main controller. We believe that those features can enable regular and independent training in home and community-based settings. Finally, the choice of the parameters and functionality of the system were validated in a subject study with young adults. Now, I will discuss our solution for addressing gap 1, which is finding parameters to increase stride lengths. We performed multiple linear regression on treadmill walking data of 14 young adults. Height normalized stride length was the dependent variable. To select independent variables, we considered sagittal angles of the three lower extremity segments, the thigh, shank, and foot, defined as shown in the top figure. 5 candidate independent variables were selected as the maximums and minimums of the trajectories of those angles in one gait cycle, as shown in the bottom figure. We found T-mean, which corresponds to the maximum thigh extension and occurs close to the end of the stance phase to be the best predictor of stride length. From perceptibility and practical considerations, Smax, which corresponds to the maximum shank extension and occurs at the end of the swing phase, was chosen as the second dependent variable. In summary, T-mean and Smax were selected as the biomechanical surrogates for stride length. Both of them had positive correlations with stride length. Therefore, to validate our choice of parameters, we had to, first, increase the surrogates by providing feedback. Second, those increases had to translate into higher values of stride length, which would finally have to improve walking speed compared to the baseline. Now I will discuss the design of the haptic feedback system. 4 features were defined as the requirements of the system. First, the system has to be modular, meaning it has separate sensing and feedback components, which should be easy to replace or repair. Second, the system has to be wearable, meaning the entire system can be worn and carried by the user. For example, it should not use a PC for real-time processing or an optical motion capture system for measurement. Further, the system should be lightweight. Third, the system should be wireless. This means that the individual sensing and feedback components should not be connected to the main controller with wires. The final requirement is user-friendliness. The system should provide a simple and accessible way for the user to control it. Given those considerations, we designed the system presented in this slide. Figure A shows the schematic of the system. Figure B shows the system borne by a subject, and Figure C provides a size reference for the components of the system. As shown in Figure A, IMUs on the thigh and shank send their orientation data to a smartphone through Bluetooth Low Energy at 60 Hz. This data is processed in real time in an Android application to find the 2 surrogates, T-mean and Smax, using a peak finding algorithm. Then, the surrogates are compared with their target values, and in case they're lower than the target, an HTTP request is sent to the ESP8266 microcontroller in the electronics unit to activate the feedback modules. The microcontrollers are connected to the smartphone through a Wi-Fi network created by the phone. Therefore, an external Wi-Fi router is not necessary. To obtain the spatiotemporal parameters in post-processing, acceleration and orientation data of the IMUs attached to the shoes were used. In its current iteration, the total added mass is 135 grams for each thigh and 120 grams for each shank. The developed Android application with the user interface shown in the figure had 4 essential functionalities. First, receiving data from the IMUs. Second, processing the data in real time to find the surrogates and compare them with their targets. Third, sending HTTP requests, feedback modules to provide haptic feedback. And finally, logging the sensor data and other events during the experiment. In summary, the design system satisfies the 4 criteria mentioned previously, and it has the flexibility to support a different number of sensing and feedback components which can be placed on different locations on the body. To validate the choice of the surrogates and the efficacy of the feedback system, a subject study with 12 young adults was performed. The walkway for the experiment is shown in the figure. The experiment consisted of 5 major trials: normal walking and fast walking, one trial where feedback was provided to both thighs for T-mean, and one where both shanks received feedback for Smax, and in the final trial, feedback was applied to the thigh and shank of the dominant side. The baseline targets in the feedback trials represented a 54% increase over the normal walking average for the thighs and 17% increase for the shanks. Also, as shown in the bottom figure for an example of adjusting its max, the targets were increased in case the subject reached or exceeded them for 5 consecutive strides. Looking at the results for the surrogates, we can see that the subjects performed better than the baseline target across all feedback conditions. And the best performance in increasing its surrogate was achieved when the subject specifically receives feedback for that surrogate on both sides. Also in the feedback conditions, the trailing limb angle, or TLA, which is highly correlated with propulsive force, significantly increased. Therefore, the first objective, which was increasing the surrogates, was achieved. Looking at the spatiotemporal parameters, stride lengths increased by at least 33.7% in the feedback conditions. The net effect was an increase of up to 19.4% in walking speed, which is comparable to the fast walking speed of the subjects. In the fast walking condition, the increase in walking speed was achieved by higher values for both cadence and stride lengths, meaning the subjects took faster and longer strides. However, in the feedback conditions, cadence decreased, but due to a significant increase of stride lengths, the net effect was a rise in walking speed. In short, the higher speed was achieved by taking slower and longer strides. In conclusion, we use a data-driven framework to find the biomechanical surrogates for increasing stride lengths. We then presented a variable, modular, and wireless haptic feedback system controlled by a smartphone, which can enable gait training at home or community-based settings. Finally, the choice of the surrogates and the efficacy of the haptic feedback system were validated with a subject study with young adult participants. For future work, we plan to evaluate the ideas above on an older adult population. For more details about the presented work, we invite you to read our paper published in IEEE Robotics and Automation Letters. Thank you.